values, and the definition, the simplest way to define them is usually different between those two. There is a kind of a general way that they both fit under, but usually you don't. That's more complicated to describe. Okay, and so there could be a, this domain might be a subset of the reals, but you could get something where the probability density function looks like this. Okay, so this would be think of this as a function f of x from this domain onto the reals. And this is kind of a drawing of like a Gaussian random variable. So this could be f of x, let's write some value here, mu, and this would be like 1 over square root 2 pi e to the negative x. This is a lowercase x minus mu squared. Okay, so this would be f of uppercase x evaluated at lowercase x. So then if I evaluate it at a spot here, the height function is going to be this value. Right? And so this is the highest value is when this term is 0, x is equal to mu. Right? So then this becomes 0, and e to the anything to the 0 is just 1, and then I just have this coefficient. So if I integrate over this function, the area under the curve is exactly 1, right? Which is what I need for probability. Okay, so now I can think of a random variable in this way. This is an example of a random variable x, where the height function is the probability density function. Okay, is this the value of the probability density function? This is a continuous random variable. I could also change the coefficient, and it's still going to be a random variable, but it's no longer a probability. The probability means that it integrates out to 1. Okay, random variable could be discrete, could be other things as well, could map to other domains other than the reals, and so forth. And then if I wanted to say some sort of event in the space, for instance, I have some event A, which is this region here, say x is between 1 and 2, right? Then the probability of A is kind of the area under the curve in this region, right? So this maps to the probability of this event A. It's this area under the curve. Okay, so this is a way of connecting these things together. Okay, so we touched on that, and the cumulative density function, which was the integral of the probability density function as well on last week on Wednesday. Okay. And we'll come back to that later in the section. Okay, so with the more, there was I feel I rushed this a little bit, some of the stuff here on Wednesday, and I just wanted to redefine a couple things that may have been confusing. Is there anything lingering questions on probability density functions? Okay, great. If there are, if they come to you later, that's fine. Just feel free to ask. Okay, the next concept is the expected value, right? So this is a really important summary of random variables and probability density functions. And so this is defined for say we have a random variable x, then then the kind of, and so this is going to be, again, the random variable is going to be a function from some domain let's say, onto the reals here. This will make sense when it's onto the reals. And we're going to say that then the expected value is kind of, if I look over all of the different probability and I integrate or I add this up, whether it's continuous or discrete, I'm going to kind of do a weighted average over the values it takes. Okay? So if, let me write this separately. There are two cases to write down. So in the discrete case, the expected value, and we'll use an uppercase E, the expected value of x is going to be the sum over, and in here we'll call, this will be, this discrete, there'll be some subset of this domain. Let me call it lambda. It's a different domain than its range. Let's see. So of all the values it could take, this value times the probability that x equals this value.
What's the sum there from? The sum
Okay, so there are all the things in this domain it can take, right? So here I'll go through an example here. So an example, let's say a die, right? So so this random variable might end up, if it's a die, so let's say it's a fair die, it takes in values 1, 2, 3, 4, 5, and 6. Okay, and let's say they're each equally likely. The probability that x equals any value equals 1 over 6, right? So for anything in this domain. So then the expected value of x is going to be the sum equals I equals 1 to 6 of I times 1 over 6. So this is these values, which is 1, 6 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6. Okay, and this is going to be equals to 21 over 6, which is 3.5. All right, so it's a weighted average over this domain. The average number you expect to roll on a die is 3.5. All right, so it's not actually one of these numbers, which is fine. Right, it's a weighted average over those. If I change the probability, it's not a fair die, and 6 becomes larger, so all these other needs to become smaller, then this expected value is going to increase. Right, so if, okay. Right, and then if I have a continuous distribution, then I need to define this instead using calculus. It's going to be the same, but with calculus, I need to do some integral. So it's an integral over this domain instead times, and then I have to define this with the PDF. Okay, so now I need to use, this is the PDF of x. Okay, I don't, because it's continuous here, each actual possible outcome, okay, is not going to have an actual probability, right? It has this PDF value of its likelihood. Instead, and these have the case that if I integrate over them, they integrate up to 1, but any given value, this area is too narrow for it to actually have any individual probability. But I can integrate them, but if I were to do this, remove the lambda here in front, it would integrate to 1, because it's a PDF. But I'm weighting it. I'm weighting it by its value. Okay, so if I if you want to know the expected amount of rain on an average day at the airport over the year, right? You could create the rain that falls on essentially the average the rainfall from every day, right? And you take the probability of the day as 1 over 365, and then you take this average. Okay, and this is the rainfall on each of those given days. Okay, the other way of doing it would be to kind of rainfall is continuously happening. So at any given time, I can have a rainfall, and I can look at any given instant, and I can kind of, this becomes either some value which is, it could be 0, but it could also be some continuous value. I guess that's a kind of confusing application example. So if instead, the other example I'd given was about this so like the Swiss train, right? And so we had the Swiss train from 137 to 0 to 138, 0. And I said that this range in here up to 137.40 accounted for 80% of the probability. And so there's probably a probability density function here that looks like this. Okay, and so then I know that up to here is 80%, but the average time is probably going to be somewhere in here, right? So so the average time would probably be a specific time, let's say 25 seconds into the minute, where kind of the way to think about it is that if you balance this weight, there's a bunch of spaghetti on top of the plate, and the plate doesn't weigh anything, only the spaghetti does, and I put my finger over right in the middle here, it's going to balance. Okay, that's one way of thinking what the average is. Okay, but you can work it out according to this calculation. If you have a continuous distribution and you don't have like a closed form of working with it, it can be hard to kind of compute the actual expectation. Okay, if you have a Gaussian distribution, it turns out it's symmetric on either side of mu, which means that mu is exactly going to be the expected value. Okay, so typically with continuous kind of distributions, someone has done some calculus and figured out what the expected value is, and you can look this up on Wikipedia and so forth. With the normal distribution, the most important one, it's given as a parameter of the distribution.
Question.
Yep.
So what would lambda be in that example, Swiss train example?
Yeah, so lambda would be a specific time, 137 and 20 seconds, would be an instance of lambda.
Okay.
Yep. Great. Okay. Erase this for. Okay, so one of the most important things about expectation is that this E is what's called a linear operator, which means that if I know something about the expectation of kind of like some parts of some complex process, I can kind of I can kind of separate those parts. Okay, so that means that I can factor out these components. So let's say I have two of these random variables, x plus y. Then I can write the expectation of x plus y is equal to the expectation of x plus the expectation of y. Okay, so I have two random variables, x and y. I don't know, if all I know about them are their expectations, then I know that the expectation of the sum is the sum of the expectations. I can decompose it this way. Okay, this will not be true of all kind of operations we do on random variables, but the fact you can do this with expectation is pretty important. Okay. Also, if I have a scalar value, then I know that the expectation of alpha times x is going to be equal to alpha times the expectation of x. Okay, I can factor this out. Okay, so this will also be important. And in fact, one of the reasons this is important is that multiplying something by a scalar is like changing the units, right? So if I change the units, that kind of naturally factors out the expectation, which is important because that's natural. Okay, let me talk about an example with height. Okay, so let's say that I'm measuring the average height of some basketball players. Okay, and I'm interested at their height on the court. And a funny thing about basketball players, if you look into this, is they wear different size shoes. They get a different amount of height on their soles. And it varies kind of widely. I guess you have more control if you don't have too much soles, but some people want to be taller and they wear really big soles. I don't know if there are rules against this, but it varies. And a player tends to get used to certain height soles. And maybe there are certain companies that make soles. So let's say that I know that the average height with no shoes is going to be mu, and let's say this is 1.755 meters. Okay? But then the shoes that they wear, okay, so this is based on the shoe companies. They tell us what type of shoes they sell to basketball players. And this is going to be a discrete random variable. There are different models of shoes. And this is 1 centimeter. I'll write this as a table. 2 centimeters equals 3 centimeters and 4 centimeters. And I can write this as a probability table and say this is 1, 10%, 10%, 50%, and 3%. Okay. Okay, so 50% of the players wear 3 centimeter shoes. 30% wear 4 centimeters, and some wear 1 and 2 centimeters, both 10%. Okay, so what is the expected height? The expected height, so with shoes. Okay, so now we can answer this question. So and this is a random variable. I'm just going to call this the raw height. Okay, so let's say it's a Gaussian distribution, and this is the mu parameter in it. Okay, so now I can say that the expected height is going to be let's say so meters. Okay, so the expected height in meters is the raw height plus the height for shoes, but this was in centimeters. So I want to say the height in centimeters. Okay, so this is the raw height times 100 plus the height of the shoes. The shoes is measured in centimeters right here, which is good, but the raw height was measured in meters, so I need to translate it to centimeters. So I need to multiply this times 100. Okay, so by linearity of expectation, I can write this as 100 times the expected raw height times the expected height of the shoes. Okay? This one I know is exactly 1.755 meters. So this is 175.5 centimeters. And then the shoes, I can write the expected value here. The expected value of S is going to be 1 times 0.1 plus 2 times 0.1 plus 3 times 0.5 plus 4 times 0.3. Okay, and this is going to turn out to be exactly 3. Okay, so plus 3, and now the answer is 178.5 centimeters. Okay.
So for this, are we assuming that there's no sort of like interaction or dependency between the two random variables?
It does not matter. Even if taller players tend to wear taller shoes, that it doesn't matter. That's the power of linearity of expectation. Okay, even if there's relation between these have a joint distribution, which is non-trivial. They're not independent from each other as well. It's still, I can always do this. Okay, right. So that's a great question because that's exactly why this is like so powerful. Okay, basically, if taller players tend to wear like taller shoes, well, you know, it's the average height. I'm just adding everything up anyways. So think I'm stacking all of the players head to toe, kind of with shoes, including with shoes. So it doesn't matter if I swap who's wearing which shoes. The total height is going to be the same, and then I divide through and take the average. Right? The probability is dividing through in the right way. Okay. Okay, so the next kind of a concept you've seen before is like the variance. Okay, and the variance, and so this is defined of a random variable x. So we'll write in this class var of x. And so there are these two equivalent definitions of this, which uses the expected value as the expected value of x minus the expected value of x squared. Okay, and equivalently equal to the expected value of x squared minus the expected value of x quantity squared. All right, so these two are equivalent, and I'll derive the equivalent just just in a second. You know, what's important to note is that with linearity, I can take out addition and I can take out multiplication by a fixed scalar. But I can't take out like squaring something inside of expectation. Otherwise, these two would be the same thing. Right? If I could take the square to the outside, if that was an illegal thing to do, then these would always cancel, and it would always be 0. It wouldn't make any sense. Okay. Okay, so the fact that you can take addition and multiplication by a fixed scalar out is special, right? And this is kind of an example of things that you can't do. So you have to be careful about when you try and factor stuff out. You can't take out the product of two random variables, for instance. You can't make that as the expectation of the product of their expectations. You can't set those equal to each other. Okay, so what is this doing? It's kind of saying I'm taking an average over the values of the random variable in their difference from the expected value, and I'm squaring it. Okay, so I had my example Gaussian distribution before. Okay, and I have a particular value of the random variable, lowercase x, and I know that and this is the PDF f of x, right? So I know that the expectation of x is equal to mu right here in the middle. Okay, and as I vary over here, I'm writing down the distance from mu, right? And I'm weighting it, and it's an expectation, so I'm weighting it by the height function, right? So remember, this is an integral over these lambda values of these lambda taking on the value x times, and in this case, it's going to be the difference between lambda and mu squared. Sorry, no. This is the value I'm taking expectation of, right? So minus mu squared times the PDF at mu, right? So the height times the difference from here squared. So as I get closer to here, this term becomes smaller, right? Okay. And it turns out this term becomes larger, but okay. Okay, so that's what it's saying here. It's kind of the average squared deviation. In expectation, what is the average squared distance that I am from the mean? Tell me about how far away am I from the mean. Okay, so let's do the derivation of why these are equivalent to each other. Okay, so to see this equivalence, okay, so the first thing you do is to expand out this the square inside of the expectation. So I'm going to have x squared minus 2 times x times the expected value of x plus 2 here plus the expected value of x squared. Okay? Right? This turns out is a fixed constant. This is a constant scalar. So I can do this, and this is all inside of an expectation. Okay? So now I can break this down, use linear of expectation here, and I'm going to get, I can break it down into the 3 terms. The first one is x squared, right? Now I'm going to subtract 2. This is a scalar. This is also a scalar. So I can factor out this one. Okay, and then what is left is the expectation of this guy here. Right, so this guy is factored there. Plus the expectation of x squared. Actually, this is a scalar. Remember, I have a scalar. I square it. It's still a constant scalar. So I can actually remove this expectation that pulls out. Okay? And now I just simplify this term. Now these are scalars, so I can multiply them together. And then this cancels. And I'm left with this version of it. Okay? Okay, so the variance is nice in the following sense, that you can factor stuff out in a similar way to linearity of expectation, but not quite as nice. Okay, it's got some properties here. So if I have a random variable x and a scalar alpha, then I know that the variance of alpha of x is going to be alpha squared times the variance of x. Okay, so I can pull out a scalar, but when it gets pulled out, it's squared. Okay, the reason for this is that what I'm talking about here is the average squared distance from the mean. That means that the units are changing. I'm talking about a squared distance, or a squared meters, squared centimeters. And so when I change by a constant factor, I'm changing the units. That gets pulled out in the squared version. Okay, so it has this nice property. It turns out like working doing analysis is going to be easier with the variance. Because of properties like this, but it's a little bit hard to interpret. And it's the average squared distance, and I don't quite know what squared distance means. I'm changing the units from what I'm typically talking about, like centimeters. I'm talking about squared centimeters. Squared centimeters is kind of like an area. What does an area have to do with heights of basketball players, right? So what we typically work with instead is, or we speak about, is the standard deviation. So, and this is typically written with the sigma. This is equal to the variance of x, the square root of that. Okay, so this is easier to think about. The standard deviation is basically the square root of the average squared distance. It's in the right units. It's kind of roughly the average amount of distance I am from the mean. Okay. Because the variance is kind of the nice thing to work about and talk about, you usually have this form, and this is in the same units as the mean and the expectation. So it's easier to kind of communicate with a non-statistical audience about the standard deviation instead of the variance. Okay, so if the variance or the standard deviation is large, that means that the probability distribution is more spread out. And if it's small, it means it's more narrow, it's more concentrated. Okay, and in 2 weeks, we'll start talking about how to kind of quantify the amount of concentration of these distributions. You know, as I mentioned, these PDFs are sometimes these not very accessible ways of representing these random variables, right? I drew this Swiss train example, and they had this kind of weird curvy line, and I didn't even know how to, in front of you, do a calculation of the expected value. I just drew a curve up there. I can kind of guess and kind of eyeball it. And so if you have a normal distribution, you have something you can talk about specifically. And sometimes you just have the expected value and the variance, or the standard deviation, associated with that. And these can be summary values that are useful in conveying kind of what's going on. But we'll look at other ways to kind of quantify these distributions without having full access to them. And this will be important in data analysis where that might not be the case. Either sometimes just knowing the expectation will tell you something about how well an algorithm is working, Sometimes you need the expectation and the variance. Sometimes you also need kind of a hard upper limit. I'm saying I know that my error never goes past here. There's never been a basketball player taller than 7'9" and shorter than 5 feet tall in the NBA, something like that. So I have strict upper and lower bounds where the Gaussian kind of trails off to infinity. Okay, and they're kind of, and these give you different powers in analysis, but they don't tell you the whole thing about the PDF necessarily. And so sometimes you don't have that. Sometimes you can only estimate it by kind of making samples and other kind of things we'll see later on in the semester. Okay. One more thing about this, the covariance. I have two random variables, x and y, and then the covariance of x and y is going to be equal to the expectation of expectation of x minus expected value of x times the y minus expected value of y. Okay, and this kind of starting to talk in a continuous way. It starts to let us know about joint random variables. This is one of the first things we can say about this. I need to integrate now over x and y in order to do this, to write down this expected value. But these are, again, scalars. What this says is that if the covariance is large and positive, that means as x is large and positive compared to its mean, then y will generally also be large and positive compared to its mean. And if one is negative, the other one is more likely to be negative. If this is large and negative, it means as one grows, the other one shrinks with respect to their means. And if it's 0, it means I generally can't say much about it. Okay, that if one grows, I don't know much about what the other one is doing.
How is this different from like correlation or like Pearson correlation? It seems like you're describing the same thing, essentially.
Yeah. So, okay. I don't want to say for sure. I might get something wrong. I think correlation is I think correlation has to do with observed data as opposed to random variables. But I might be getting this wrong. So I will look this up and then I will be sure and I'll tell you next lecture. Yeah, it's a good question. Yes, we aren't doing much on kind of classical statistics and so forth in this class, and we'll see why. We're going to look at kind of this cross-validation point of view to measuring kind of importance of something as opposed to a statistical point of view where these Pearson correlation scores show up. And we'll get to that later in this semester. Okay, well, let's maybe quickly do variance here. On this example, I left this up. So the variance here, remember the mean was 3 centimeters, so that it's going to be the expected value of s minus the expected value of s squared. Remember this term is 3, so that means the expected value of s, or the variance of s is going to be the sum over, let's see, 1 minus 3, let's reconcile the sum, is going to be 0.1, which is the probability, times the distance squared, that's 1 minus 3 squared, so I'm going to have 4 centimeters squared, plus 0.1, which is the probability of having 2, and this is 1 centimeter squared, plus 0.5. But that's S 3 centimeters minus the mean. It's exactly the mean. So times 0 plus 0.3 times, again, the difference is 1 centimeter squared. Okay, and so then the weighted average of these is going to be I know this is going to be 0.8 centimeters squared. Okay, and so that means that the standard deviation of shoes is going to be square root of 0.8 centimeters. So the standard deviation in the shoes they wear is going to be this. Okay, so the last kind of topic I need to cover today is going to be for basically continuous random variables. How do we talk about these joint, marginal, and conditional variables? Okay, so for in the discrete setting, you could write down a table and you could kind of define these naturally. For in the continuous setting, you know, it's have to be a little bit more careful with calculus. Okay, so let's say I have two random variables, x, y, and so I'm going to talk about the joint PDF between them. So I could, so they're joint PDF. We'll say f of x comma y, and this will be from some domain of x and a domain of y to say 0 to infinity. Okay, so it's going to be to the subset of the reals, and it's a PDF, so it has to be positive, and it could be arbitrarily large, as long as the integral it's a PDF, so the integral of it, the two-dimensional integral, has to be 1. Okay, and so in the discrete case, then f of x, y, say for values lowercase x and lowercase y, is going to be equal to the probability of x equals x and y equals y. Right, so if I had this table over the values of x and y, this is essentially one cell in the table. Right, so this was the joint PDF. But in the, and then there's the marginal PDF is going to be a useful tool here. And so in the discrete case still, okay, so we're going to say that I can get this marginal PDF, right? So I'm going to marginalize out y. I just want to talk about x, but maybe I'm only given the joint PDF. How do I get this? I sum over all values of y on the joint PDF of x and y. I'm going to say it's the sum of all the probabilities for the different values of y as long as x takes on this value. Right, and so this is equal to the sum of all the values that y can take on times the probability that x equals x, y equals y. Okay, and so right, so just so this is clear, I've got a fun example, and then we'll talk about the continuous case. Okay, so I had a story. So I had this friend from college who was kind of organized in like his own way, and he didn't really like folding his clothes, so he just threw all of his clothes in a pile. This included, he did distinguish the clean clothes and so the dirty clothes. Okay, and if everything got too smelly on average, he washed everything, threw them back in the pot. Okay, so this, and then every morning he would take out a random pants and shirt. Okay, and but maybe these weren't this. There's some interesting joint probability. They may not have been independent. So let's say the shirt could be green, the shirt could be red, and the shirt could be blue, and the pants could be blue, or the pants could be white. Okay. Okay, and so let's say the probability he had a green shirt and blue pants was 30%, 5% chance white pants and green shirt, red shirt and blue pants was 10%, red shirt and white pants 2%, or 20%, 20% blue shirt and blue pants, and 15% blue shirt and so white pants. Okay, and so now I want to know the probability. I'd like to know the so if I want to know the marginal distribution of the shirt, right? So f of s. Okay, the marginal distribution for the shirt, the probability that you wore a green shirt is going to be 0.35. I just add up these two columns, right? The probability of red shirt was going to be 0.3, and the probability of blue shirt was 0.35. Okay, I can also write down the conditional probability. So the distribution of P given the S. So let's say the probability that given that the shirt is equal to red. So I say given that you wore a red shirt, what's the probability distribution over the pants? Okay, that is narrowing down the probability distribution. Right? Remember, we could draw that shape that, you know, we had this kind of geometric view of it. Now I'm saying I know the shirt is red. So I'm looking, this is the whole table, and I need to normalize by the marginal value, 0.3. Right? So now this is going to be equal to another table where I have pants equals blue and pants equals white. Okay? And this is going to be 0.1 divided by 0.3, and this is 0.2 divided by 0.3, which is 1/3 and 2/3. Okay, so this is, I get the conditional by normalizing out by the marginal. Okay, so these marginal and conditional are related to each other. Okay, and I can do the marginal distribution over pants as well by summing these up. This is 60% and for blue pants and 40% for the white pants. Okay. Okay, so the real trick now is to do this, to write this down for continuous random variables. Okay. Okay. Okay, so with these continuous random variables, the reason why to do this is that it's hard to write down what the joint PDF is with continuous random variables. But I can write down what the joint CDF is. Okay, I can write down what the joint CDF, this is the cumulative density function. Okay, and that's going to be a capital F of xy, takes on some values x and y, and this is going to be, this is a probability that capital X is less than or equal to lowercase x, and capital Y is less than or equal to lowercase y. So I can write this down as a probability in some clean way, that both of these things need to be true. X the uppercase x, the random variable, needs to be less than whatever I specified, lowercase x here, and same, and also same with the random variable uppercase y, to be less than whatever I specified for lowercase y. Okay? And then I can say that the marginal CDF, okay, f of x, right? So now I want to factor out the y, and this is going to be the limit as y goes to infinity of f of x, y. Right, and similarly, I can write down the marginal CDF for y by marginalizing out x. Okay, so that's saying the probability that x is less than lowercase x, given that y is less than something arbitrarily large, that everything is less than. Right, so this one loses its meaning as the limit as lowercase y goes to infinity. Okay, so I can define this cleanly. Okay, so now I can write down. So those are nice. Again, the CDF is nice because these CDFs are probabilities. This is equal to the probability that x is less than x. I don't need to say anything about y. It's a probability. It's between 0 and 1. Integrate over all values. Well, yeah. So it's this probability of a certain specific type of event. Okay. So the joint PDF now, I have to write down in terms of calculus. Okay, so I have to take the double integral over x and then over y in order to define this. This was the same as before with one-dimensional CDFs, but now I have to differentiate over x and y. Okay, in order to find the joint PDF of this. Okay, so sometimes some probability distributions like the normal distribution or the Gaussian, which is higher dimensional generalization of it, the joint PDF actually has a closed form expression. This is e to the negative something here. But in this case, there's no closed form expression actually for the CDF. And there are other probability distributions where the opposite is true. The CDF I can write down in a closed form, I can calculate in the computer, but I cannot calculate the PDF explicitly. And you have to use calculus to go back and forth between. Okay. And now I can say that, and then I can say that the marginal PDF is going to be the integral from negative y equals negative infinity to infinity of f of xy. So I fix think I have a two-dimensional space. It's kind of this wavy, bumpy, continuous thing in two-dimensional space. I fix the x value and then I integrate over the y value. Okay, this is not a probability still, right? For any particular value x, the size of the value, the domain over x could be 0, so it's a probability 0. but this still integrates to 1. Okay, and then the conditional PDF you can write down of x. So x, so given y, x, given some value y, is equal to f of xy. So the joint probability divided by the marginal probability on y, right, which is defined the same way as x, but you swap the values x and y. And you have to kind of assume that for this value y, it's not 0. Okay, otherwise, it's not defined. Okay. I'll give one more example, and then I'm going to hand it over to the TAs to give you a quick demo and show you some simple stuff. But so we talked about the normal distribution, which is usually some random variable x, which is going to be is going to be 1 over square root 2 pi e to the negative x minus e squared. Right, you can divide by the variance here. Okay, so this is the normal distribution. There's a generalization of this to the Gaussian distribution, and we'll write this is a Gaussian. Okay, so for a value v, now v will be a pair of coordinates x and y. Okay, in 2 dimensions, but this can go in higher dimensions as well. We'll talk about higher dimensional with linear algebra, so I won't dwell on these issues, but this is squared. Okay, so the standard deviation squared it's going to be the distance between v and mu. Mu is now a 2-dimensional point divided by 2 standard deviation, right? And so this is equal to, in 2D, this is equal to 2 pi e to the negative x minus ux squared plus y minus uy squared by 2. Okay, so this is kind of a 2-dimensional bump, which I'm unable to draw well. Yeah?
So is that like top term in the exponent? That just keep putting a distance? So if you add a higher dimension, you just keep adding on those things?
Yes, that's right. Yeah. So we'll see this in higher dimensions later in the course. Yeah. But yeah, so this generalizes to higher dimensions, and it's one very nice property about it, which I'll just mention, is that every marginal version of the Gaussian distribution is still a Gaussian. It's still of this form. It may change the standard deviation and the mean, but it's still of this form. And this is a very special property about this distribution. The normal is kind of the most common form of noise model to assume on data. That if you have a data point, and I think I have some noise with it, I'd say in 1 dimension it'd be the normal, and in higher dimensions you'd say the Gaussian. Okay, so these will come up on and on and over the semester. Okay, so these are example. This is a common. This is the PDF for the Gaussian distribution in 2 dimensions, and this is it in higher dimensions with the putting distance. Okay. So good. So I have to run. I will stop here, and you guys they'll show you how to plot some of this in Python and whatever else. So, Ben went what? And then you can introduce yourself so everyone knows who you are.